because like I said, I got an email from a student that was super informative. Okay. All right, we got our enthalpy umbrella here. I'm not the greatest artist, but we're going to pretend that's the enthalpy umbrella. That has all these different terms coming out of it. All right, the rain of enthalpy is going down on our umbrella. And what things are coming out? Well, we've got things that are dealing with energy thermal. We have things that are dealing with energy chemical. And we have stuff that's dealing with energy phase change. And this is one we haven't talked a lot about today yet. Okay. So there's lots of terms that are associated with each one of these types of ideas. If we're talking about energy thermal, we know that we have little CP and big CP. One of those is the specific heat capacity. The other one is the molar heat capacity. I don't remember which one is which. I think you guys have your table with you. Specific heat capacities. One of them is the molar heat capacity. One of them
CP is specific, big CP is molar.
All right, so this is joules per grams degrees Celsius. This is joules per mole degrees Celsius. All right. So those are the units, and this is basically the amount of energy required to change some amount of that substance. If it's the specific heat capacity, it's the grams of that substance changing its temperature by 1 degree Celsius. If you're looking at the molar heat capacity, it's still the amount of energy, but now it's the amount of energy to change a mole, which is 6.02 times 10 to the 23rd pieces of that by 1 degree Celsius. All right, so those are terms that we use when we're talking about energy thermal, is the specific heat capacity or the molar heat capacity. So this one is the specific heat capacity, and this is the molar heat capacity. And those describe the amount of energy in joules that it takes to form 1 gram by 1 degrees Celsius. Right? All right, that's how you think of those things. All right, we've got energy chemical. Energy chemical, we have terms like heat of solution. It's an interesting vocabulary term. Heat of solution, generally units are going to be kilojoules per mole, because the heat of solution, now, you know what, let's go back to heat thermal, heat energy. Here, the types of problems you're going to get is a hot or cold object contacting another substance. So generally they're going to say you got a hot rod, you put it into cold water. You got a cold rod, you put it into warm water. Some enthalpy is exchanged. And in this case, in thermal energy, you just have to figure out what's the system, what's the surroundings, and you apply Q equals MC delta T. So that means you got MC delta T equals MC delta T. And this is generally like a hot or a cold thing, and the energy is going from one place to another. All right, so if we talk about chemical energy, now we're talking a lot more about Hess's law. Remember Hess's law? You got to break stuff up from reactants, and it's going to cost you energy to break those things up. Then the energy is stored in the new bonds that are created, so some of that energy goes into the bonds. Now, if it costs you a whole lot of energy to break it up and you don't get much energy stored, then energy is going to have to put into the system, right? If it costs you a whole lot and you don't get a lot back, energy is going to go in. It's going to be endothermic. The opposite is true. If it doesn't cost you much to break the original bonds of the reactants and you get a whole lot of energy back in the products, it's going to be endothermic. There's going to be heat energy going in the opposite direction. Heat of solution is when stuff dissolves, right? So you put things into a solution and stuff dissolves. Generally, sometimes it's an exothermic process, sometimes it's an endothermic process. You just have to see. Now, in this case, in the heat of solution, the system is generally the thing that's being dissolved. Right, so heat of solution, kilojoules per mole. The thing being dissolved is generally the stuff that is the mole. So you're talking about the amount of energy it takes to change that stuff. It's kilojoules per mole, so the system is generally the moles. The surroundings is often water or some sort of solute, right? The thing that's being dissolved, the stuff is being dissolved in. And that's usually the thing that you're going to use to calculate how much energy is going from one place to another, because you generally calculate a change in temperature is involved in a heat of solution. So that's one kind of heat of energy or energy chemical type of term. There's also the heat of formation. So the heat of solution is generally expressed as a delta H value, and they might sometimes put a little SOL. Does not mean you're out of luck. It just means it's heat of solution, right? Heat of formation is a different symbol. This is the delta H naught with a little F by it. Remember that table I gave you? Appendix C values? Appendix C values. Some of them were zero. The ones that were zero were the metals in solid state, or the diatomic gases. Those had a heat of formation of zero, meaning they came into existence without costing or distributing any energy into the planet or the universe. Some things that had a negative enthalpy means you had the heat was released when they got formed. Other things that had a positive enthalpy value means you had to add heat energy into them to make them to form. So this is the values from Appendix C. Now these are values that are standard values, and every textbook has these values. Some of them are different from other ones, but they're all going to be relatively standard. These are things that are used to calc the Hess's law problems. A lot of times is the heat of formation values. All right, we've also got the enthalpy of reaction. A student sent me an email with every one of these vocabulary words. What does this mean? What does this mean? And I thought, you know what? That's a really good idea to clarify and kind of categorize things. The enthalpy of the reaction is basically this idea of Hess's law, where the enthalpy of the reaction is equal to the enthalpy of the products minus the enthalpy of the reactants. Right? That's because you have to add energy in to the reactants to get the bonds to break. When they create products, some of that energy is stored in the new bonds, and the overall enthalpy, whether it's positive or negative, depends on which one pays you more or costs you more in the long run. So enthalpy of reaction is delta H values, which is always, you want to think about these as kilojoules per mole. And finally, we have the phase change types of problems that we haven't talked about yet. Phase change problems also involve specific heat capacity, because we have to know the heat capacity of things like liquid water in order to change its temperature. And we also talk about the heat of fusion, which is lab you're doing in this class, versus the heat of vaporization. Heat of fusion is generally kilojoules per mole. It's also an enthalpy value, delta H. Delta H heat of vaporization is also expressed in kilojoules per mole. We'll talk a little bit about those values in today's lecture, hopefully by the time we get to this point. All right, so there's the terms. There's summaries of all the terms. Now we're going to use these terms to do some more calculations. So when I'm throwing these terms out at you, hopefully these are ways for you to categorize the type of problem that you're going to have to do and the types of values that you're going to see in each of the different problems that you have to do. Right? Okay, so let's do some, we saw a little bit of Hess's law before, where we had the enthalpy of the products minus the enthalpy of the reactants. Let me get there's a good PowerPoint slide. Oh, here we go, standard enthalpies of formation. There's our enthalpies of formation. This is just like your Appendix C values that I already gave you too. So those are there's enthalpy of the reaction, right? The overall enthalpy, products minus reactants. So if we think about what Hess's law means, it takes things that are what we call stepwise reaction. Remember we talked about this idea of an energy diagram. And if we look at this energy diagram, the first reaction is what's over here to the left. The CH3 gas is decomposed into carbon and hydrogen gas. And so what this energy diagram, remember, is enthalpy increases up in this direction. So things that are down here have a very low energy or low enthalpy. They don't hold a lot of energy. Things that are up higher have contain more energy by virtue of the fact that they've gone through a chemical reaction. So this first one is telling you that they're starting at this part here where the C3H8 is, and you have to add 5 O2s to it to get it to absorb enough heat energy to create those things also. And if you look at the energy term here, the delta H term is a positive 103. That means you have to add 103 kilojoules of energy to get these things down here to go up to these things up here. All right? So that's the first one. If we look at the second part, now you'll see that the little pink shadow has changed. So this is a different reaction. Now we're taking the things that were the products here, and I'll show you how this kind of cancels out a little bit later. But we've got one of the products over here with O2. So here's the reaction plus the O2 gives me 3 CO2s, which is the products over here. So now, where this was an energy absorbing process, the first step, and it had a positive enthalpy value, the second step, we're going from a state of higher energy to a state of lower energy, so it's releasing some of that energy to the tune of negative 1181 kilojoules per mole. So the first step, it is absorbing energy going from this direction. The second step, it's releasing energy. The third step, if we go on to the third step of this, now we take these things that were the reactants and we put them as products over here. We put them as reactants on this side and we make new products. One more step, it's also energy releasing process. It goes from higher energy to lower energy. That energy is released. And if what we did was add all these things together, it would give us the Hess's law problem. So what I'm going to do now is I'm going to try and go back and forth and show you how these things cancel out, which is how the Hess's law problems work. All right, so if we start with this one, I wish I could do a split screen on this. I'm going to write everything on the first slide, which is C3H8. I'm going to narrate this as I write it down here. So you write it down, C3H8 as a gas. So write those symbols down. C3H8 as a gas plus 5O2 as a gas plus 5O2 as a gas yields, and you can see on the product side there, 5O2, it goes up in energy, 3C graphite, so you write 3C graphite, plus, on the product side now we're writing 4H2 gas, plus 4H2 gas, plus my last product is my 5O2 gas, 5O2 gas. Now I'm going to switch over to my ladybug and I'm going to show you what I wrote, and I want you all to be writing this down because this is going to be a good concrete example about how to solve these kind of problems. So C3H8 plus 5O2 is the first reaction, gives me 3C plus 4H2 plus 5O2. Now I'm going to have to put the enthalpy value above it because I didn't leave much room for myself. The enthalpy value on this one is, I'm going to go back to my PowerPoint now. The enthalpy value on this one is plus 103.85. So plus 103.85 kilojoules. So now if I go back to my ladybug, you all should be writing this down. I should have put, if I had thought about this beforehand, you know what, I'm going to switch this around to landscape version because it'll be easier to solve originally. It's C3H8 gas plus 5O2 as a gas yields 3C as graphite plus 4H2 as a gas plus 5O2 as a gas, and our enthalpy value is 103.85 kilojoules, and it's a positive 103.85 kilojoules. All right, so now you can see what I'm doing. I want you to follow along, and I'm going to narrate this as you do the same thing. All right, so now we got our first one. Now we're going to write our second reaction. So now we have to start with the reactants that we started with, which was the 3C graphite. So 3C graphite, you're going to write down as your first reactant, 3C graphite plus 4H2. So you're just going to rewrite the products from the previous reaction, 4H2 as a gas plus 5O2 as a gas, which yields, now our new products are at a lower energy level, which is 3CO2 as a gas. So you're going to write an arrow, which yields 3CO2 as a gas plus 4H2 plus 2O2s plus 4H2 plus 2 O2s. And my enthalpy value there is going to be a negative value because we're going down in energy, which is negative 1181 kilojoules. So a negative 1181 kilojoules. And I'm going to go back to Ladybug so you can see what yours should look like. All right, Facebook friends, I'm trying to teach here. Back to the Ladybug. So far now, you can see what I've done. I'm going to do the same thing. Now I'm going to take my products here, and that's the third step of my reaction, 3CO2 gas plus 4H2 as a gas plus 2 O2s as a gas. Right? Same kind of thing. Now I'm going to go look at the third step here. I started with my reactants. Now my products are 3CO2 as a gas. So you should write that, 3CO2 as a gas plus 4H2O liquid. Right. And then what that gives us is this overall reaction. So I'm going to show you how we calculate the overall reaction. Don't write the overall reaction. What I'm going to show you is how we figure that out. Oops, I didn't get my enthalpy value from the last one. What was that enthalpy? Negative 2220. All right, negative 2220 from the last enthalpy value.
Wait, wasn't that the total?
Did I mess up? I might have. Let me look and see.
1143?
No, the total enthalpy is going to be the difference from where we started here to where we ended.
Oh, yeah. So
I did mess it up, didn't I? 1143. I think you're right. 1143. Thank you. Thank you. Negative 1143 kilojoules. Thank you. You're right. That is the overall enthalpy. All right. So now look at it this way. Fix everything. Now this is sort of like algebra. In algebra, you sometimes combine equations and cross out like terms. That's exactly what you're doing now. You're going to combine these three equations, cross out like terms, and the like terms are what we call intermediates. They do not show up in the overall final equation. So anything you cross out is called an intermediate. This reaction doesn't go straight through from reactants to products. It takes place in a series of 3 different steps. When you get to Chem 152, you're going to learn about kinetics, which is the rate of the reaction, as well as reaction mechanisms, which tells you why each of these 3 steps happens independently of each other. But before we go there, and next semester, let's just talk about Chem 151. All right. We're going to combine like terms. So let's see, what do we have that's the same on both sides that we could cancel here? I think I got some graphites I can cancel, right? I got those graphites I can cancel. What else can I cancel here?
3CO2?
Not everything. Not everything.
Cancel.
We got
4H2.
some CO2s we can cancel, some gaseous CO2s, right? There we go. And they got to be on both sides. They have to be on opposite sides. Think about these like an equal sign, all right? You can't cross them out on the same sides. They have to be on opposite sides.
Okay.
So
4H2.
Oh, the 4H2.
let's see. I got a 4H2 there. Yep, there we go. You guys are eagle eyes. What else?
Another 4H2 and then
There's another 4H2. There's a 4H2. There's a 4H2. Get rid of those H2s. What else?
the 5O2 and 2O2.
502s.
So
502s.
everything in the middle. And then 2O2.
We've got 202s. Is that it? Well then, hot diggity dog, here we go. Here's my overall equation, and I don't even have to look at the slide because you can see what I'm doing. How am I getting the overall equation here? Whatever's left that didn't cancel out. What are the things that I canceled out called? Intermediates. Be one step ahead of your peers when you get to Chem 152. Now, how do you suppose we deal with these values to get the overall enthalpy change? Add them up. It's just the sum. So you take a positive, that number, a negative, that number, and a negative, that number. And when you add them all up, the value should be what the overall enthalpy change was for the individual steps, right? And that should be, what's our overall enthalpy change? What should it be? Negative 2220. Guess what? There's another way to calculate this. If you use the heat of formation values, the delta heat of formation not values, how would I calculate the enthalpy of this reaction if I just had these values and I didn't have the steps? Appendix C. And I would say, okay, the enthalpy of the products, right, minus the enthalpy of the reactants. So I would take 3 CO2s, I'd add them to 4 waters, I'd figure out the enthalpy of that, and then I'd subtract the enthalpy of one of those and 5 of those, right? And what number should I come up with? The same number. Whoa! So you can calculate them either way. Be prepared on the exam. I might ask you to calculate it like this, and I'd give you the heat of formation values. I might ask you to calculate it stepwise. Now, let's do another problem that's not exactly like this, that's a little more difficult out of your textbook. So electrical homework problems that you're going to have. Hot diggity dog. All right, homework problems. Let's see, I picked one out here. Here it is. Here's the one I'm going to use. I'm just going to copy it directly on the paper. It's homework problem 5.61 in your textbook. All right, so 5.61. I like to use landscape on these kind of problems. It says, from the enthalpies of the reaction, I would advise you to write these down because I'm going to ask you to calculate H2 gas plus F2 gas yields 2HF gas. The enthalpy of that reaction is equal to negative 537 kilojoules. Next one, carbon as a solid. I'm going to put these a little bit far apart from each other because we're going to have to do some manipulation. I would ask you that you leave some space. Don't put them right next to each other on the same line. Give a couple of lines in between. So carbon solid plus 2 fluorine gas come together in a combination reaction to yield CF4, which is also a gas. And the enthalpy change for that reaction is negative 680. The third one, I got 2 carbons as a solid plus 2 H2s as gas, which yields C2H4, also as a gas. And my enthalpy value for that one is plus 52.3 kilojoules. Now, our target equation, that's what this is called. You have a couple of labs coming up. This week you're doing heat of phosphoric acid. That's a chemical energy 1. Acids and bases added together increases the heat of the solution. You just figure out the Q that went into the solution that had to come up from the phosphoric acid. You figure out kilojoules per mole. The next one is the heat of fusion for ice. We'll talk about that today or Thursday. And this is the type of problem you're going to have to do 2 weeks from now. This is the Hess's Law problem, and you're going to have to be expected to learn how to do this and know this and have it in your back pocket before you come into the lab, because it's one of those project ones where you have to kind of figure out your methods on your own. All right, so our target equation, they'll tell you this in the Hess's Law lab. Our target equation, this is how I like to put them. They say it's C2H4 as a gas. Write this down. Plus 6F2 as a gas, which yields 2CH4 as a gas. Let's see, whoopsie, CH4 as a gas, plus 4HF as a gas. And they want to know what's the overall enthalpy of the reaction. Well, if we had an appendix C, we'd go in appendix C and figure out all these and take the products minus reactants, but we don't got appendix C. We're going to pretend we don't got it, so we got to do it based on these reactions. Now, you have to use some of your algebra skills, because it's just like in algebra. If you want something on the other side of the equation, you flip it. So for example, if I have to flip one of these equations to get one of the reactants on the opposite side, what do you suppose I'm going to do with the enthalpy sign? I'm just going to switch the sign. So if I have to switch this and have HF yield H2 and F2, I simply change that to a positive 537. Say, for example, I need more than one of those things and I want to multiply the whole equation by 3. I'd have 3 H2s and 3 F2s making 6 HFs. What would I do to my enthalpy value? Multiply it by 3. That makes sense, right? Okay, so now let's look at this problem, kind of step back and say, here's what I want it to be looking like when I'm done. So I either got to flip these back and forth, or I got to multiply them by some factor, so that every one of these individual stepwise reactions adds up to this beast down here. That's my target equation. So I start looking at this thing and I go right off the bat, I see C2H4 as a product over here, and I need it as a reactant, right? So right off the bat, I'm going to swap that. I'm going to flip it, but I also need to do something else. Oh, no, do I need? No, I don't need to do anything else. So I'm just going to flip this whole equation. So I'm going to say, all right, instead of C2H4 in the product side, I'm going to just cross that, a single line through it. C2H4 as a gas now is going to decompose into 2 carbons as a solid plus 2 of these H2s as a gas. Remember, what are we going to do to my enthalpy sign now since I flipped the reaction? It's going to be a negative 52.3 kilojoules. All right, well now I got my CH4 in the right place. Let's see. I got the F2s on the reactant side, although I need more of them. CH4s, where's the CH4s? Am I missing CH4s? Did I copy this right?
CH4.
Supposed to be CF4.
We don't have
2C. I might have copied it wrong. I might have been looking at the wrong 2C.
CF4.
C2H4. From C2H4. 6F2s, 2. CF4. See, that's what happens. Walking and talking. Mess myself up. And 4HF. Okay, does that make things better? I think so. All right, so what do we got to do? I got CF4s on the product side, but I only got one of them, so what should I do to this thing? Multiply the whole banana by 2, right? All right, so I'm going to say I got 2 carbon solids plus 4 fluorine gas, which yields 2 CF4 gas. And what am I going to do with my enthalpy term? Multiply it by 2, which would be what, 1360? Is that the right math? I'm trying to do it in my head while I'm talking and writing. All right, so let's see. We got the C2H4 on the right side. We got 6 F2s? We got 4. We need 6. Do we need to cancel some of these hydrogens out anywhere else? We got hydrogens on a product. Oh, here we go. All right, I think I need to do something with this top equation. So what should I do with the top equation? Multiply by 2, same thing. So now I'm going to go 2 H2s. This is going kind of fast, I realize. I'll post this after class
Okay.
so that you can go through this again and again, which gives you 4 of the HFs as gas. And then what am I going to do with my enthalpy term? What's 537 times 2? I can't do that one in my brain. It's 1,074.
Yeah.
I can't do it in my brain. 1,074 kilojoules. All right, we're going to cross that one out. All right. These are kind of fun. Yes?
Why did you flip the third equation but not the first two?
The third equation. I flipped it because I see down here I need C2H4 as a reactant, and in this equation it was a product. So I had to swap it because I want to get the C2H4 over here. Good question. Yes?
Wouldn't it have to be multiplied by 4, not 2?
Who?
Because down below it's 4HF. Or do you?
Well, let's see what happens. Let's see what happens. So what do we got that cancels? Are we canceling things yet? I think we're almost to the point of canceling.
Isn't delta
Let's
H
see.
for number 1 negative?
Yeah.
Right. Oh, see, talking and walking. Thank you for policing me, you guys. I used to give my high school students a free pencil when they found me doing a boo-boo. What is? It's negative. Thank you. Thank you. Thank you for keeping me straight. Walking and writing and talking at the same time messes me up. All right, so what are we going to cancel here now? I think we got carbons. Do we cancel carbon anywhere? I think we cancel carbon. So here we go. There's a carbon cancels. Some hydrogens. There's a hydrogen. Where else is another one? Here we go. Got 2 there to cancel. What else? We've got to cancel some fluorine. Where is fluorine to cancel? Did I miss them?
It's down below.
Oh, you add them up. Here we go. That and that adds together to make
6.
6. This one comes straight down two CF4s, that comes straight down, and the HFs come straight down. Whoop-doo, we are done. And look at that. Dang, I'm good. Exactly 11:15. All right, so what number do we need? How do I can't figure out my enthalpy value here? I take this number, a negative 1074, this number, a negative 1360. Thank you guys for keeping me straight. And this one also, they're all negative. Hot dog, that's going to be a big honking negative number. So this is an endothermic or exothermic reaction. Since they're all negative, and when you add them up, it's going to be negative. That means it's exo. Exo. Do we add them all together? Yes, ma'am. You add them all together. There you are. You got the tools to do all the homework. We'll do one more kind of problem on Thursday and another quiz. Practice that homework. Oh, there was one boo-boo on one of the homeworks. I think the homework today, I posted it. There was one where you needed another piece of information. I posted the piece of information you need. So go and look. If you got your homework, it's the second problem. I think you had to have time to
You guys want to make a group chat, dude? You guys want to make a group chat? You have any questions?
I posted the fix, so check and make sure, because there will be one problem, you won't have enough information to solve the problem.
482, 46, 34. You want to put in the group chat? If you have any questions, we'll have to study. Sure. Sure, James. I'm gonna. You guys have WhatsApp?
I'm using WhatsApp and Instagram.
On the exam, what I'll do is
After using Facebook.
Do you have WhatsApp? Yeah. Alright, I'll do it.
it's posted, right? It said posted, fix on the home, just print out the Okay, about 2 minutes. The homework that's due today, it's due on Thursday. If you send me an email and ask me for homework 6 and homework 7, I will send them to you. One of them is already posted on Canvas, so if you just go on Canvas, in the announcement, it's posted as the new homework.
I made it here, you know.
Remember there's a boo-boo, I fixed it, so you can print that one out. Just send me an email and ask me for homework 6, which is what it's due today.
So,
Oh, I'm sorry, sweetie.
Yeah.
Then you can finish that one. When you leave it.
That's all we have so far. That probably
I
one.
was still at
Already?
have this on.
y'all granted it, but I didn't know whether it was done.
So,
You take a picture of it, don't take it.
Take a picture of it. Look at it.
No, I'm just trying to figure out.
I can just print either that or copy that.
I just got a photocopy thing, procedures all done. The data table's all done. Discussion and conclusion, and then I took a picture of what happened in there. I can write it up. If you don't got time, I might be able to write it up.
You got signature?
Oh yeah, that one that I had before.
Obviously, this is the quiz, you get to drop
What you
one.
doing, copy and stick on the board?
No, you gotta, on the board, just like, he's telling you what needs to be in there. And you start writing.
Tuesday's the exam, and then Thursday you do the exam back,
You got right
so.
conclusion.
Yeah.
Be back after that probably? Okay, well then, if you had to miss, this is probably no time to do it, you're missing a whole lot of instruction, you're just, and anything I do, I always post. The lectures, I record everything, which reminds me I should turn this off because it's still recording. All right, well, there you go.